Let us welcome Anton.
Thank you very much, Derek. Today I'm going to talk about verifiable computing in Haskell. I'm going to touch upon three things. Firstly, what is it? Then, why do we want it? And then I'm going to kind of give a description of the general process, and then a more detailed description of the first bit of the process. Right, just some conventions I'm going to use throughout this talk. Public information is going to be in blue, private is going to be in red. Right, fairly straightforward. Okay, motivation. Why do we want this? We want this so we can efficiently verify the correctness of computations without executing them. That's it, pretty much. An example of this could be, say Alice has some query U, and Bob has his private W, which could be a database, for example. Alice wants to know the result of some public function Z, which operates on U and W. Now, Alice wants the correct answer, and Bob doesn't want anyone to know what his secret is. So how do we do this? Right. But first, some example uses. One use could be proving you have some preimage to a hash function. So this could be proving you have some password that gives rise to a certain hash without sending the password down the wire. It could be proving you have some file. You can prove you have a file that gives rise to a hash without actually without sharing the file. Another example could be proving you're part of a group without revealing your identity within the group. Another one could be proving you have enough money in your account for a specific transaction without revealing your actual account balance. And then the last one, which I think is probably the most interesting, is if you have an auction, you can prove who won the auction without revealing any of the bids. I think that one's particularly interesting. All right. So the general approach is, first we need to take some arbitrary computation and put it in the right form, so that we can say that whether it has been correctly executed is equivalent to some mathematical expression. And that's kind of going to be the focus for today. But when we've got it in the right form, we then need to run this form with our private inputs. So in the example previously, it would be Bob's W, and then yield a proof that each part of this form was executed according to the pre-shared form, which would be the function f, going back to the previous example. Okay. And then there's a bunch of mathematical wizardry that is really, really complicated that I'm not going to cover, but just makes it work. Yeah. So just some of the underlying things that I'm going to explain, so which are the underlying mechanisms that allow it to work in the first place. The first one is partial homomorphic encryption. So what this basically means is performing a limited set of operations on ciphertext, as if you were performing them on plain text. For example, actually you may be familiar with group homomorphism. For some crypto schemes, this also works for encrypted values. Okay. So let's ask the age-old question, what is the floor area of my shed? We know that the width and the length, right? But we're not very good at maths. So we want to offload this to some cloud. So enter the cloud. We've got the shed floor area solver TM. We've got our private width and length. But we don't want to share our width and length because it's kind of private to us. And how dare the shed floor area solver TM know how big our shed is? Okay, so RSA to the rescue. So RSA has this property where this multiply operation on two encrypted values is equivalent to this multiply operation on the unencrypted values. So if we just give ourselves a public and private key, and then encrypt our private values using the public key, and then we get this 2 and 126 value, which are our new width and lengths, but encrypted using our public key. We then send that to the shed floor size solver, which then does the computation on those values. And then we receive those values, and then we use our private key to decrypt that and get the actual result. Okay. The next thing that this uses is what's called pairing crypto, which is a bit more complicated and is not really the subject of this talk. Several talks could probably be given on it. The basic idea is that you can move these two exponents, you have to find the correct e, but with this correct e, you can actually move the exponents out of. So these are actually group generators. But yeah, there's a link for more info if you want to find out more about that. Cool. So in the real world, what does this process look like? Well, the verifier generates this circuit representation and shares it with the prover, and this is taking your function and then putting it into some form, and then the prover evaluates the constraints, which is this circuit representation, using the homomorphic encryption that I just described earlier, and then obtains the output, which is the result, and then a witness, which is kind of proof that they ran this circuit representation correctly, and then the verifier, using this pairing math, does it to the homomorphic output that the prover just gave them to verify the witness. All right, that's just the general process. So I'm going to just detail how to create a simple circuit compiler, something that can take a problem like this and make it so you can prove this without having to re-execute it, and then you can have some more complicated computation, something that is not just a maths equation, because nobody wants to write maths equations for programming. That's the general idea. So so we're just proving that we evaluated this with these two inputs. Okay, so the first step is we want to represent that actual equation, so we can just make a very simple expression type. The var name is for the inputs, the lit rational is for the literal values, so the 36 in that example, and then we just got this bin op thing, which can either be multiply, addition or subtraction over two other expressions. And then if we can, with the help of a num instance, we can then write the same problem, unrolling r to the power of into a multiplication, just like that, which is quite nice. Okay, so the first step in turning our kind of equation into these circuits is we turn it into like kind of a single static assignment form, where the possible forms are x equals some constant, x equals some other variable, and x equals some operation on two other variables. Right. So if we take our m squared, we're gonna turn that into m times m, and we're going to introduce a new intermediate variable which is called b. All right, and then for our constant, we're going to assign c to 36, and then a is going to be the result of b plus c, and then the result itself of this equation is going to be a minus n. Cool. And then you can represent these constraints in Haskell just deriving a gate type. We call it a gate because it's kind of like a circuit. So the constraints are either setting some variable to a constant or setting it to some other variable. And then you've got kind of a gate has an output, input, and then two inputs. Cool. And then here we're going to build kind of some mechanism for walking through the expression and then giving a bunch of constraints from that. So we're just going to define some data structure, which is going to have our supply, which we're going to use to generate the names for the intermediate variables as we walk through the expressions. This is kind of like the Hindley-Milner type inference. And then our constraints, which is just going to be a list of constraints that is going to grow as we walk through our expression. And then we're just going to have our builder monad, which is just going to carry the constraint system. And then we're just going to specify our starting state. And then this names function will just literally generate fresh variable names. So how it works is kind of unrelated, but just will generate all the way a to the z. It's an infinite list of a to the z, then AA, and then so on. So you never run out of variable names. And then fresh, what it's going to do, it's going to get the value in the supply and then increment it by 1, and then index this infinite list of variable names by whatever value was in the supply. And then emit is just going to push a constraint to our list of constraints. Everyone follow so far? Yeah. Cool. And then onto the actual mechanism for doing the compiling. So compile is a function that's going to take some variable, some name to assign the output to of some expression. So if we're evaluating a var, then all we do is we set the output just to be whatever the value in the var is. If we are evaluating a literal, then all we're doing is adding a constraint that the output is equal to this literal. And then if we're doing a binary operation, first we're going to check if it's a variable. If it's a variable, we know that it's already been evaluated. If it's not, we're going to create a new intermediate variable, which we're then going to compile and then return the result of that as the inputs to the binary operation. Okay. And then with the help of some pretty instances, we can pretty much get what we wanted earlier from our expression. Next stage, 2 rank 1 constraint system. So, we can represent each one of these constraints as a set of 3 polynomials, and the idea is that we construct these clever polynomials so that it's only 0. So the result is 0 on correct inputs. So and then so that it satisfies. So yes, y is it represents the output of some constraint, and v and w are the 2 inputs. And then if it satisfies this, then we know that where S is a witness, or like a proof that we have ran the constraint correctly. And if that equals 0, then we know that someone has. So just to compile it, so our expression b equals m times m. So v and w, they represent the 2 things on the right-hand side. So we're just assigning them to 1 to indicate they've been used in this case. So m and is set to 1 for v, and m is set for w, and then the result actually ends up in b. So we set b to 1. Cool. And then we can represent that same structure in Haskell, just like so. So the v, w, and y is just a list of vectors, but they're actually polynomial coefficients. And then we have one rank 1 constraint for each constraint. Cool. And then we can just write that in Haskell by having this function called uses, which for every single variable. Actually, it's important to note that these variable names are just arbitrary. The result is where we're going to store the resulting variable. M and N are our inputs, and then A, B, and C are just the intermediate variables we introduced earlier. And then 1 is for putting constants, or literals, like the literal 36. So yes. So here we just have uses, which for every single variable, if it matches some string, will give us 1, otherwise it'll give us 0. So in this case, we want if it's m, we want it to be 1. So we look at the input 1, and we set it to 1 if it matches the input 1. And then we do the same for input 2, and then we do the same for the output. And then for setting constants, this one translates to actually minus 36 times 1, and then there's some magical polynomial magic that I don't quite understand, but that works as the rank 1 constraint, and it satisfies. And then we can just add a condition, some new code to handle that case. And the last one is just doing A equals B plus C. So we say A is the result, and then B and C are the inputs. And it's only for multiplication gates do we have a V and W value. It's different for addition. We just use the top vector, and then when we're doing subtraction, as I will show, Okay, so that's the implementation for addition. And then for subtraction, we just use -1. And then because it's the result, we set y to 1. Okay, yeah, so that's how you would implement that. And then if we run this against the constraints that we generated earlier, we get these list of v, w, and y values, which are what we want. And after that, we need to be able to check this rank 1 constraint against something, because how do you prove that you ran it successfully? And what you do is you generate what's called a witness. And a witness is an assignment to all variables. And the way you arrive at it is you execute each of the flattened constraints, here I've written commands, and set the values as you go. So our initial state with our input. So remember we said m is 2 and n is 3. You can think of that as just a vector, and then you have the 1, m, n result, a, b, c are the columns. So the first one we're doing b equals m times m. So we set b to the value of m times n, m times m, which is 4. And then c equals 36. That's quite simple. We just set c to 36. And then a equals b plus c. We set a to b plus c. And then we set the result, which is 37, to c minus n. Cool. And then we can implement the checking process just like so. So all it is this witness that is that. And what we do is we do the dot product of that against the v value, and then the dot product of that against the w, and then the dot product of that against the y. And if the v times the w minus the y equals 0, then we know that the program was executed correctly with the witness that was given. Cool. So if we do that, we get a list of true values, because all the constraints, they are satisfied with a witness. But checking each gate individually is not a fun process. Or in a real system, you might have millions of gates, because you'll have some more complex computation that will be compiled into this, but it's not very productive to have to check each one individually. So you do what's called Lagrange interpolation, which just allows you to turn that all of those individual rank 1 constraints, which is one for each circuit, into a single one, and that's kind of quite interesting, but I'm not going to go into that because it gets a bit complicated. Cool. So the next thing you can do to this simple language is you can introduce Boolean operations. So we're just going to add and or an XOR, and there is this is quite a nice thing where you can, if you say 1 is true and 0 is false, then you can basically get the and or XOR just using arithmetic, just like so. And then we can just add a new function called binop, which takes some binop, the output, input, and other input, and if it's and, then it emits a multiplication, just like we were doing before. And then if it's or, it introduces 2 new intermediate variables, and then does the multiplication of the first 2, does a multiplication of the inputs and assigns that to one of the intermediate variables, and then does an addition of the inputs and then assigns that to another temporary variable, and then does a subtraction of the 2 things it just computed, just like we did there. And then XOR is just implemented in the same way, so we subtract the 2 inputs and then we multiply the result. And then for the inputs that we had before, we just do the same old thing. Cool. So it's really important to add that what we just did was a really big simplification of the process, like really big simplification. When you're actually doing this, you don't do it over like regular numbers. You do it over elliptic curve elements, over a finite field with a prime modulus. So what are those words? Elliptic curve elements are coordinates on a curve that looks like that is defined by this equation, where that condition is true. There are specific ways of doing addition, multiplication, and subtraction that are defined for this curve. And then over a finite field, instead of a real curve, you have a set of discrete points. So you're just restricting the amount of points you have to more atoms there are in the universe, but you're still restricting it. And you have some generator that, when you do to the power of, it'll cover every single point. Every single point there is in this set of points. So the final verification, this is more complicated. The final verification step in the real world ends up as this is basically the God equation. If this is true, then you know that someone has executed the program correctly. The actual operation you're doing is you're just moving these exponents. You're just moving the exponents. So if you just look at the pairing functions that I talked about earlier, you can probably find more information about that on the internet. Yeah, but this isn't really the subject of this talk, because it's a whole thing in itself. But yes, it is computationally feasible to construct a forged proof. Questions? It's kind of brief. Yes? Yes, thank you. Yes. So just a disclaimer, I'm no means an expert on this, so don't kind of...
So do you actually need to pass the witness as well?
Yes, yes. The result of evaluation is the result and a witness that comes with it, and then you use that to verify that someone executed the pre-shared circuit correctly. Yeah. Does that answer your question, sorry?
Kind of, because from what I understood, you can create the witness from the computation, right?
Yes.
Or do you need the inputs as well to create the witness?
You need the inputs as well. Because the idea is that you're proving that you ran some program with certain inputs. Yeah.
So to clarify, basically you said that you wouldn't like to check your to prove that every gate works correctly, and it means that checking state the witness state after every gate proves that the gate was not forged, right?
So yes, you end up with a witness, and the witness works against every single gate.
Yeah. Okay.
And then
how do we transition from this array of states to Lagrange polynomial Lagrange?
Oh, okay. Yes. So what we do, if I go back to, let me go back to something. So for every single v value for all our circuits, we create kind of, so the Lagrange interpolation is you have a set of points, and then you want to get a polynomial that crosses through every single point, right? So what we do is we take all the v values for all of our circuits, and then we have some, and then we have just 0, 1, 2, 3, 4, 5, just incrementing numbers as one of the other coordinates, and then we get a single which goes through all of the states. And if you evaluate it as a single point, then you get that specific state. But then what you can do is the verifier picks a secret point that it knows. Yeah.
Can you sketch how the auction would work?
How the auction would work? No.
Oh, what do you learn in the auction? You only learn if you lost one? Or?
You only learn who won, I think. But you don't learn it. The idea is you don't learn the bids, I think. Yeah. Oh. Yeah. Oh.
Okay. So where does the V, W, and Y come from? So
okay.
These polynomials, where's the origin of those? Does the verifier choose those, or does the prover choose those?
So the the verifier, when they're, it's part of this like form that the verifier produces, so the verifier. Let me go back to the. So the verifier generates the circuit representation, which is all of these circuits, basically. Does that answer your question?
Yeah. So
okay.
They generate these polynomials, but and then they send them over to the prover.
They send them over to the prover. Prover evaluates them using its private inputs, and then sends the result back to the verifier, and then if yeah.
Right, because the whole idea is that the prover doesn't want to disclose its secret information, right? But the verifier wants to know about it, right? So they construct this circuit, and then the prover uses all its private data along with the polynomials that it was sent,
right?
And then sends back some result and a witness. And then the verifier uses some super special algorithm.
Yeah, I mean, the verifier doesn't necessarily have to generate the circuit representation. It could be either party, but it's just like a pre-shared thing that is decided on. Yes. Yes.
Is there a way to generalize this to effectful computations, even in limited form?
Pardon?
So if you are running it on the cloud,
right?
Where a company
yes, you want to
do some effectful computation. Is there a way to extend this?
Ooh, that's an interesting question. I don't know. I think is yes. Yes.
I may not be following completely, but the prover now has to calculate and a witness. Is there ever a situation where calculating the output is still computationally feasible, but kind of calculating the witness then becomes infeasible, like it adds such an array to computation?
So the thing is, I think this idea was initially proposed in like the 90s or something, and it's only in like some recent papers that they actually made it optimal. And I think the way that they made it more optimal is the form of the circuit, which is kind of used here. Yeah, but it's still kind of not very efficient. Like, I think Zcash, which uses this as one of the mechanisms, their circuit representation is like almost one gigabyte for their program or something. But yes. Yeah? You?
Is there a result regarding the relationship between how expensive the computation you want to do is versus how expensive it is to prove the witness and send it back? Because it sounds like the whole idea of proving is several orders of magnitude more expensive than the computation that you want to do.
Yes. So there may be some cases where that cost is okay if you really do want to have some computation over private data, but you don't want to reveal it, but it still needs to be done.
Is there a mathematical relationship, something like if my computation is polynomial, then the whole
verification? So actually, the cool thing that this has is the verification is done in constant time. It can be done in constant time because you're doing a single. The production of the proof. I think it's probably linear to the size of the. But actually, the Lagrange interpolation step is like O(n) to the power of 2 for the number of circuits or something. Yeah, that's the most optimal way. But the intuitive way of doing it is like O(n) to the power of 3. But using like some fast Fourier transforms or something, you can get it better.
This might be okay, right? Because the whole idea is that the verifier is the one that doesn't have the computational power.
Yes.
So if the prover has like orders of magnitude more computational power, even if they have to work like orders of magnitude harder, it still may be like the relationship between them still might be reasonable.
And actually, the circuit representation that you're generating, once it's been generated, then for a certain program you don't need to generate it again. You just plug in the inputs and go. Any other questions?
Yeah. So practically, where is this being used?
So Zcash is one. There's the kind of the big paper this comes from was called Pinocchio, which is kind of a big implementation of this. There's also, I think it's called V something tiny RAM, which is like simulating a computer using this, which is.
Use it for electronic voting.
You could, yes, you could have a voting system where it reveals who won without revealing who voted for who, and then how much. Yeah. Any other questions?
Yes, sorry. Would you mind explaining again how the process kind of goes? So you have the two inputs and your witness, which was kind of produced using the inputs and the computations as if they were private keys, right?
So,
Produce the witness.
so yes, the witness is produced. Sorry, pardon?
Yeah. So you have the inputs and
Yes.
the witness on
The witness.
one side,
Yes.
and then you send it to
The
to someone that's going to do the
Yeah.
computation with the input, with the encrypted inputs,
right.
right? And then, do they do anything with the witness? Do they change the witness?
So the person who does the computation gets the witness as a result of doing the computation, but there only exists a witness for a successful execution, pretty much, of the computation. So, sorry. What?
So the verification that the correct computation was done is done using the witness.
Done using the witness, yes.
Exactly. So the witness is sent back from whoever did the
From the cloud or something, yeah.
So you don't send then the witness in the first place.
No. The witness is after the cloud has run the program and got the result. It'll send the witness and the result to you, so you can see that the witness so you can see that the cloud ran your program correctly. Any other questions? No.
Has the implementation been fully verified?
I don't know. Probably not.
Could you write a programming cock and get it to produce some Haskell code?
Probably. Yeah. Actually, there's I can do a demo. That's probably very, very small. See that? Oh, it's still changing the font size. Too much. Anytime? Okay. That's all right. Any other questions? Oh, well, doesn't like that. Okay. Click it again. Is that readable? No, probably. Yes. So just right. No, okay. So we can do something like. Let me just bring up the example. So that's the only thing that we can see. So this is just a kind of just a checksum that has some starting value as the input, and then so the buffer. This is doing a checksum of whatever is given in the buffer, which is a list of, in this case, of some values. In this case, rationals, and then for every single variable in the buffer, it will assign it to a temporary variable and then sum it to some accumulating state. So this is kind of the most basic checksum that you can do. And if I run this, see, and then kind of do well. Hello London Haskell, and then our starting state. Oh. Yes. Then this should. Oh. Okay. Yes. Okay. So that unrolls the for all for every single piece of data in the input, and then creates a bunch of circuits for that. So we first get our expression, which is just successively adding the ordinal representation of each character. Then that's turned into some constraints. and then that's actually compiled to a rank 1 constraint system, and then it is ran, and the result is 1,954, and then it checks whether the witness matches the rank 1 constraint system that generated earlier. Yeah. Yes.
That's a very basic question. So can you go to slide 3 or 4?
Pardon?
Can you go to slide 3 or 4 or something like that, where you had Alice and Bob having a little conversation?
Oh, yes.
Maybe, yeah, this one. So in your floor plan example, shared floor plan.
The floor plan is just
No,
an...
go back. What's U? What's U?
This doesn't map to the floor plan example.
Okay, so U is...
This is just some example by itself.
But if you wanted to do this,
Yes.
how would you incorporate? So Alice has to be able to ask a question.
Yes.
How would you do that?
Well, in this case, Alice's question is public.
Okay, but what if she wants to ask a specific question? That's on your applications slide. You had a bunch of stuff where people can ask specific questions, right?
Like what? Sorry. What?
Well, you had a database. Bob has a database.
Oh, okay. Yes.
So how
would you influence?
incorporate-
How do you make it a bit more practical?
Well, how do you ask a specific question? How do you have inputs that?
Okay. So I mean, you could represent your query just using numbers or something,
So those would be inputs in the constraint system.
Inputs into the constraint system. Yes.
So Alice gets to fill in some variables.
Alice gets to fill in some variables. Yeah.
Is it that the query U is always in this form of like this polynomial equation? Like you first, like your question is basically has to be reduced to a certain form, right? Like so, it's not that you're asking arbitrary questions. It's basically you're supplying like arbitrary polynomial equations. Like times
that would not be true because then I could discover your floor plan. Yeah, then I could discover your height and your.
Actually, the floor plan is just partial homomorphic encryption. That's not verifiable computing or.
Okay, so but the polynomials are
stuff.
Polynomial is F.
Yes.
Right?
Pardon?
Polynomial is F.
Yes. Yeah.
The polynomial is U.
No, because then I could discover.
So remember,
if Alice can supply any polynomial she wants, I can just supply the polynomial which is F.
I think U is the input.
And I can learn what M and N are.
Okay, I think F is the polynomial. U is the inputs to the function.
A subset of the variables.
Yes. So in the case.
W is another subset of the variables.
Pardon?
So W is one subset of the variables, and U is another subset of the variables.
Yes. Yeah. So in this example, we're just when we actually evaluate it and generate the witness, we are setting M and N values there.
But those are W right now.
No, the M and N are pardon?
The secret.
They're not the secret. M and N are the inputs that we want to be computed.
But your question is supposed to be secret, wasn't it?
Pardon?
Those were computed supposed to be secret.
So you could have other variables that are that only the person who's executing would have. Yeah.
Okay.
Yeah.
Okay, so M and N are supplied by Alice.
M and N is supplied by Alice. Yes.
So Alice's question can be public. Like the question is public.
Yeah.
It's the private data that the prover has. That's not right.
Yeah.
So like her question, her polynomial can be public.
It can go, but you can't specify it.
Well,
if you could, there wouldn't be any secrets.
No, it's this idea that you have the polynomial plus the private data.
So you use the polynomial, and you have a witness which if given to the polynomial, will equal 0, which it proves that you ran the computation correctly.
So basically it means that Alice supplies some kind of like encrypted variables with Alice's public key.
Yeah.
And Bob uses public key to encrypt his like secret knowledge. And then all the inputs are fed into this circuit
Yes.
and the computation
And then-
is run, and therefore only Alice can decrypt.
Yeah, so you could do that. You could also do the homomorphic encryption on top of that. Yeah. Yes.
I was trying to understand is the witness, the type of the witness, it's basically the set of the constraints?
No, the witness is just a list of assignments to all the variables in your program.
Okay. And
which, when given to the fancy polynomial you build, proves that you executed your program correctly.
Okay.
And the witness.
So you can verify the witness in theory in constant time, but
yes.
That time would actually also be linear with the size of the program, I guess, because the bigger the program, the more assignments you will have.
Yes. Yes, I think so. Yeah.
And I was also trying, like, the original kind of like idea to basically be able to prove something about the program without having to execute it. I mean, the verification is done without executing the program.
Yes.
But the
yes.
proof in this case, it's actually.
You have to execute the program to get the proof.
Okay. So
yeah.
I guess that would be kind of like another problem that maybe it's more specific or something.
I think the idea is that making a proof without executing the program is impossible, and that's why it works. yeah.
And you also mentioned that there was a link or two in this presentation.
Yes.
Where is the link? Is it on GitHub?
Yes, there's one more for more information about paying crypto.
Yeah,
and
I mean like the link to the slides.
The link to the slides. Oh, the slides are public. You can go to that URL. But yes, I'll put it. We'll put it in the comments of the Haskell meetup.
Okay, perfect. Thank you.
The example you run, was it on the simplified implementation or in a library that implements it fully?
It was on a not a library that implements it fully, but a more complicated one. Like, for example, the type of variables is actually parameterized. So instead of it being over like a rational variable, it could be points on an elliptic curve. Yeah. Yep. Any other questions?
Should we give a large